4 exponent rules. I'm going to go through the exponent rules. You could do some practice with a partner. See, this other page right here has some practice problems. So knowing the exponent rules is important. And then after lunch, we'll go back and hit on some graphing and graphing practice. You don't have to know the names. So the only reason this is called the product rule or the quotient rule is just because there's a multiplication problem or a division problem. So you don't have to know the name of the rule, but you just have to know what it simplifies to. So x to the 5th times x cubed, if I wanted to write out repeated multiplication, x to the 5th would look like that. X cubed would look like that. How many x's are being multiplied together total? Because I don't have to write a multiplication symbol there. I could write a multiplication symbol in between every single one of these x's, right? Because multiplication is commutative, forward and backward, any order. So how many x's are being multiplied together? This is really x to the 8th power. So if I take x to the 5th and I multiply by x cubed, I really have x to the 8th power, as long as the base is the same. This can't have a base of x to the 5th, and this have a base of y cubed. But as long as they have the same base, you can add them together. So the rule is, if the base is the same, you're allowed to add your exponents together. What's going on over there? Did you find one, or? Fraction. So if I write out this next problem, which is x to the 4th over x cubed, I would have x to the 4th on top, x cubed on the bottom. How many of those x's can I cancel? Right? Anything divided by itself gives you 1. So I really have 1 times 1 times 1 times x. So I really have x to the 1st, or just x left, right? I have 4 x's on top, 3 x's on the bottom being multiplied. Cancel 3 of them. So what did I just do with the 4 and the 3? I really took the 4 and subtracted the 3, right? So a to the n minus m. I should have written that. So to me, if you just have a one-off rule, it's not a lot to memorize. But if you now have like 4 rules, you probably don't want to just memorize the rules. You want to know how to write it out and just check what the correct rule is. So if you're multiplying, you can add. If you're dividing, you can subtract. Do these seem familiar? Like once upon a time, you might have learned these exponent rules? Maybe? Yeah? I hate to ask, but power rule. This is distributing a power into a function inside some parentheses. If I wanted to write this out, this is x squared times x squared times x squared. That's what cubed means, right? Take the number and multiply by itself 3 times. What is x squared times x squared times x squared? Use the product rule from up at the top. Isn't that xx times xx times xx? So how many x's do I have being multiplied together? X to the 6th. So we would just write that as x to the 6th. Go back to the beginning. What could I have done to the 2 and the 3 from the very beginning? So the rule is, if you're distributing, you can take it and multiply your exponents together. But now we've got addition, subtraction, and multiplication, which might get confusing. So you always want to be able to write it out to check the answer for yourself. Those are the 3 biggies. To me, the distributive power is just that you have to distribute it to everything inside the parentheses, and you know that rule anyway. So if I had 2 things inside the parentheses, a to the n times b to the n, they both get the exponent. The one that gets forgotten is the number. So see how I have 3x cubed? I actually have 3 squared times x cubed squared. So they both get squared. So I'd really have 9x to the 6th. So I had to distribute that 2 inside the parentheses. The other thing you can think of is really get squared. That's the one that's going to get forgotten most of the time. The other one, just distribute it inside the parentheses. So you'd have a to the n over b to the n. But what I have for that last one, do your distributive property and multiply. So this would become x to the 6th, and 3 times 4, this one would become y to the 12th. You cannot say that the 6 and the 12 are going to divide. This base is x, this base is y. You can't do anything else to that and cancel anything else. All right, so lots of rules. So just practicing with these rules. The ones on the back, we've already talked a little bit about the negative exponent rule from our table of powers that we did last week. It's the reciprocal of the number. So you're allowed to flip it upside down. And so I wrote, why is that? So let me prove it to you a little bit. So it says, let's simplify the following if we were going to use repeated multiplication and canceling. So I would have a cubed on top, and I would have a to the 4th on the bottom. Cancel, cancel, cancel. What are you left with? You're left with a on the bottom. So I can write that as 1 over a. Are you with me on that first part? I multiplied a times a times a, and then a to the 4th on the bottom, canceled them. So I want to prove to you that this is the same thing, because now I'm going to use the quotient rule. What was the quotient rule from the front page? I could take the 3 and subtract the 4. What is 3 minus 4? 3 minus 4 is negative 1. Didn't I just show that those things have to be equivalent? A to the negative 1st power has to be 1 over a. So they are the reciprocal of each other. If you have 45 to the negative 1st power, you just have 1 over 45. There's no negative sign. The negative just is the reciprocal. So leave it positive. And then this would just be 1 over positive x squared. You're just taking the reciprocal. And then the last rule that we used like all the time last class for graphing was that anything to the 0 power is 1. And I just wanted to prove it to you another way. Remember in the table I was showing you that it has to be 1? Because if I have all the powers of 2, 2 to the 1st is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, right? We're multiplying by 2 in this direction. In this direction, we're dividing by 2. So in order to get to this side of the table, when you divide by 2, you get to 1. So this would be 2 to the 0 power, 2 to the 1st, 2 squared, 2 to the negative 1st. So another way to prove the 0 property is, let's do again repeated multiplication and canceling. So if you had a cubed, you have a times a times a over a times a times a. Well, that cancels, that cancels, that cancels. Anything divided by itself is 1. So that is equivalent to 1. But what if we did the same expression using the quotient rule? So what if I took 3 and subtracted 3? Don't I get a to the 0 power? So I took the same expression, simplified it 2 different ways. These have got to be equivalent to each other. Anything to the 0 power is always 1. So these last two are really easy. If you see something raised to the 0 power, that's it. The answer is 1. This whole thing is being raised to the 0 power. So its answer is 1. Anything raised to the 0 power is 1. So before you try a few on your own, I just want to take a look at number 13, 12 and 13 are good, I guess. Take a look at 12 and 13 just because they have a couple things going on here. So on number 12, see how you have all these negative exponents? Before you simplify, you want to make all your negative exponents happy, positive exponents. numerator, and the 2 is happy where it is, because 2 already has an exponent of positive 1. That's just kind of imaginary there. So I'd want to rewrite this 2x to the 7th over x to the 4th before I do anything. Now I can simplify. So if I have 7 of them on top and 4 of them on the bottom, how many can I cancel? And if you want to write it out for yourself, what would 7 of them look like? And what would 4 of them look like? So 4 of them are going to cancel, and I have how many left in the numerator? So I'd have a total of 2x cubed left as my final answer. Yeah, the 2 is still sitting there, and then 7 minus 4 is 3, so I have 2x cubed, x cubed right here. So let's try one more together before you go through and see if you can evaluate these. On number 13, before you start the problem, we are going to move anything that's negative down to the denominator and leave anything that's positive in the numerator. See how these two are already positive exponents right here? So we're going to take the 3 squared, take the reciprocal so that it can be in the denominator. X times x to the 4th is going to stay in the numerator. X to the 12th is going to come down to the denominator. So these are all positive exponents now. We have to simplify the expression, right? So what would you do to simplify the expression? Okay, can I do it your way in a minute? Because I think people get confused when there's some things that are negative. So when there are some things that are negative, we will get the same answer over here as adding, but I think people won't understand necessarily where that 3 to the negative 2 went. I'll show them a different method in a second. I just think before I start simplifying, if I don't have any negative exponents, it makes it easier to not make a mistake. So how many x's do I have in the numerator? I have x to the 5th total, right? How many x's do I have in the denominator? I have x to the 12th total. So where do I have more x's? Denominator. So my x's are going to be left in the denominator. How many will I have left after I cancel 5 of them? I'll have 7 of them left in the denominator. So you need to write your answer as 1 over 9x to the 7th. And to me, I feel like students make fewer mistakes if they move the negative exponents at the beginning. So I think what Elise was suggesting is to just leave it all with the negative exponents at this step. Did you do the 3 to the negative 2 in your head and just make that 1/9, right? And then this is x to the 1st, plus 4 would be 5, minus 12 would be negative 7. But then you still have to write your answer without any negative exponents. So as long as you know that the final answer would look like that, you can write it that way. To me, I think students can see better that, okay, I have 7 of them left in the denominator. So when I write my final answer, x to the 7th is in the denominator. So as long as you can take this and write it like this, that's fine. As you go through them, you can kind of pick which method. As long as you're going to get it simplified at the end. Actually, there's no really negative ones left. When you try the homework, you can use either method. Okay, here we go. Here are the answers to the guided practice. Pause it if you need to pause it. Go. Okay, so if you are looking at your graph, actually here, I will look at my graph, leave my graphs up here, and you're going to look at your notes for that page. So the back of page 30, was it back of page 303? So it says, let's compare the graph of 2 to the x. Can I get rid of this now? So it says the graph of 2 to the x, y equals 2 to the x. What would be its domain, range, 0.03. Okay, so I'm looking at this graph and I'm thinking about what the domain and range would be. Can I go forever side to side? No, it goes forever, right? Anything to the 0 power is 1. So I can go forever side to side, right? So the domain of an exponential function is all real numbers. What's the range of the function, though? I have this asymptote here, and then I've got everything above it, right? So your y values would have to be greater than 0 for your range. My y-intercept, anything to the 0 power is 1. Is this graph increasing? So as I read it from left to right, is it going up? Yes, it's going up, right? Increasing. The horizontal asymptote is the equation y equals 0. Does anyone know if it's discrete or continuous? Have you ever heard those terms before? What does it mean? You know, stats maybe? Discrete data means that you don't know what's going on in between, but you have specific points in time. But this is actually continuous because I could raise 2 to the 1.7 power and it would be somewhere in this region, right? So it's a smooth curve that is continuous. And then you can just kind of sketch the graph of what it would look like. And then what's it on the other side? What's it say? Oh, 1/2 to the x, right? So y equals 1/2 to the x is this graph. Here's 1/2 to the x. So guess what? The domain and range in y-intercept are all exactly the same for this function, right? I can go as far as I want left to right. My range is still greater than 0, and my y-intercept is still at 0, 1. So they actually have quite a bit in common, right? These first 3 pieces are in common. Y is greater than 0 and 0, 1. So here's something that they have that's different. It is a fractional base is a decreasing function. So as I read it from left to right, it's getting less. So this one should be decreasing. But it has the same asymptote, right? Still at y equals 0. And it's still continuous. And it kind of looks like that. So those are facts that you can apply to any exponential function. You're going to need to know the domain, range, intercept, asymptote, what it looks like. So let me just write that under on this next page. And then we'll talk about kind of the bottom in 1 second. So the domain is always all real numbers. The range is always y is greater than 0. The y-intercept is always 0, 1. Growth is increasing. Decay is decreasing. They're both y equals 0. They're both continuous. This one goes up, this one goes down. All right, so it says, do any of the facts change if the base is like 1/2, 1/5, 4, 8, 100, right? If I change this to a 4 or 100, all of these facts would stay exactly the same. So the only thing that changes is the steepness. So only thing that changes is the steepness. If you have 100 to the x power, it's going to be really steep, right? Because now it's 100 squared or 100 cubed instead of 2 squared or 2 cubed. And then down here, I was just reviewing your transformation rules from Unit 1. So they have not changed. Their job hasn't changed. But if you notice that the A value isn't really included down here, right? Because the A value is just the steepness of your curve. But the B value over here or over here moves the graph up or down because it's outside the function. So if I add 8, I'm going to move it up 8. If I subtract 8, I'm going to move it down 8. And then see how the C value is inside with the X. So X plus C would move left X minus C would move right. X plus C, X minus C. And then it says the plus or minus in front determines a flip over the x-axis. You remember that from quadratics and square root graphs? And if you put a negative in front, it determines if you're going to flip upside down. So before you turn the page and try some of these, let's just look at a few and see if we can remember what they would do. So anyone want to tell me, what do you think this x plus 5 does? That's 5. What does this one do? Flip it upside down, right? If you want up over the line. So if the original function looks like this, the new function would look like this. This is the other flip that you might see. So that's making all your x values negative, right? So that flips it over the y-axis. And the reason for that is, isn't this the same as this? 1/2 to the x is that dotted graph, right? So these are flipped over the y-axis. This is flipped over the x-axis. Upside down. And what's this plus 7 do? Up 7? So some of those rules you might have to like put back into your memory, but this is kind of like in parentheses. That's where it's opposite what you think. Plus 5 goes to the left, minus 5 goes to the right. This is outside the parentheses. So this is up 7 or down 7 based on the number. And I will stick to like simple one-step transformation kind of on this page. So we're going to just do it with 2 to the x. But on a quiz or a test, I might put 3 to the x or 5 to the x, because the only thing that changes is the steepness, right? If I pulled out like 5 to the x, what are 3 key points that would lie on this curve? Anything to the 0 power is 1, right? So if I made a little chart for myself, you can always do -1, 0, and 1. Anything to the 0 power is 1. What is anything to the first power? Just itself, right? So 5 to the first power would be 5. And what does a negative first power do? That takes the reciprocal, so you get 1/5. So you get 0, 1, 1, 5, and then 1/5. So it's like that. The only difference is when you're at 2 to the x, you're only going up 2 and you're only going 1/2. So these are all 2 to the x graphs. So what I like to do to start graphing, oops, I like to put my parent function on the axis. So 0, 1, 1, 2, and -1, 1/2, that would be my parent function. Just the next page of 303. Right, this was the back page of 303, and this is just the next page, isn't it? Okay. What does that plus 3 do? What does that plus 3 shift everything? Left 3. So I'm just going to go 1, 2, 3 to the left, 1, 2, 3 to the left, 1, 2, 3 to the left. So I've shifted left 3. So the only thing I need to include is my dotted asymptote, which would still be at y = 0. So that would be the type of graph that you might need to do on a quiz. I was going to do it Wednesday, but we might do it Thursday. We'll see where we're at tomorrow. We might be able to do it after lunch on Wednesday. That might be good. Okay, let's do the next one together. What does the next graph say to do? Take 2 to the x and do what with it? What's this plus 3 do? Up 3. So I like to put my parent function back on the axis, right? Because this would be 2 to the 0 power is 1, 2 to the first power is just itself 2, and 2 to the negative first power is the reciprocal 1/2. So that would be the curve. I'm taking all those points and I'm just shifting everything up 3. So 1, 2, 3 up, 1, 2, 3 up, 1, 2, 3 up. So what else is going to shift up? So if you shifted everything up, you also have to shift the asymptote up as well. So if the asymptote was at 0, now the asymptote will be at y equals 3 because it also gets shifted up. All right, see if you can try 3 and 4. Can you shift 3 and can you shift 4? Think about which flip. We kind of read them over here. If you aren't sure about the flip, flip over the x-axis, flip over the y-axis, or on the board. Kind of do these 1 or 2 step transformations. The homework 3-1 has you match the equation with the graph. Matching the equation with the graph. So you're trying example 3. You're taking the original function and flipping it over the x-axis. I'm going to put number 3 up there. So if I was going to put my original function, it would look like that. So if I'm going to flip it upside down, it would just be those 3 points flipped upside down like that. So there you go. And then it would be y equals 0 is still the asymptote that it got flipped over upside down. What are your 2 transformations on number 4 that you're going to do? Down 4 and flipping it around over the y-axis. So you can do it either way. I like to flip it over first and then shift it down 4. But you could also shift it down 4 and then flip it around. So that would be my kind of flipping it over. And then I'm going to shift it down 4. 1, 2, 3, 4. 1, 2, 3, 4. So the important part of your answer to number 4 is what is your y asymptote now? It would be at -4. Because the asymptote was originally at 0, so now the asymptote is down at -4. Sometimes people get confused because they see the intercept. The intercept is only at -3, right? So when you're trying to write equations, remember, your intercept is always one above the y-axis, or sorry, the x-axis. So it's the axis itself that shifts however many units, right? Down 4 units. Okay, the last thing that we haven't touched on today, this actually might be completely new. You might have never seen this before. So I'm introducing it today, but we need lots of practice on this stuff tomorrow. So I'm going to kind of have a day in between because tomorrow I was going to start doing the quiz review. I think we need a day in between. So we'll plan on a quiz Thursday instead of Wednesday, just because I think we need more practice. But the fractional exponent rule, I want to show it to you today so that tomorrow we can do lots of practice with graphing and the exponent rules and fractional exponent rules. Just because you need kind of drill It's just drilling on these skills, right? Do them 20 times each. Has anyone ever seen fractional exponents before? I'm not sure if you got to it in Algebra 2. This is page 305. So you've actually always seen a fractional exponent. For example, if I told you 4 squared, what would you tell me the answer to 4 squared is? We know 4 squared is just 16. So, nope. So we just evaluated 4 to the 2 over 1 power, right? So 4 squared is the same as 4 to the 2 over 1. So up till this point, all of these denominators of these exponents were always 1. Now you have a denominator. The denominator is what's creating a square root in the problem. So the denominator for this problem is n. N is the index of the root. It might be a square root, it might be a cube root, but the denominator is what's new. So it says a fractional exponent means you find the nth root of the expression and you raise it to the mth power. So the bottom is the root and the top part is the power. So in the past, you've only ever worried about the top part. 4 squared is 16. I never really thought about the denominator. So the denominator is what's new. And usually students haven't seen this before. So this might be new to you. But 25 to the 1/2 power is not 12.5. 1/2 is not a coefficient. 1/2 is the radical for this problem. So the 2, because it's in the denominator, flips out here, it's called the index of the radical. And then this is just the first power. The 1 is in the numerator. This is just the square root of 25. What is the square root of 25? Just 5. So on your calculator, if you typed the square root of 25, or you typed 25 to the 1/2 power, oops, I didn't type it correctly, 25 to the 1/2 power, it would still tell you the answer is 5. So a fractional exponent is just another way of writing a radical expression. So on number 2, the 2 is on the bottom, so that's the index, and then the 3 is the power because it's in the numerator. Does anyone know 16 cubed in their head? I don't. But I do know the square root of 16. So you can do it in either order. I recommend doing the square root first, because isn't the square root of 16 just 4? And now I know what 4 cubed is. 4 times 4 times 4. You should know that one from your power families. So 4 times 4 is 16. What's 16 times 4? It's 64. Very good. All right. You just get that off the top of your head? Good. You're on it. Exponents is your unit. All right. So number 3, let's put that together. The 3 is going to go on the outside. So now we have a cube root and then 27 squared. I don't know 27 squared, but I know the cube root of 27. What times what gives you 27? So that's why you got to know the power families for the cubes. 3 cubed is 27. So this is equivalent to 3 squared. So you're going to have to kind of memorize some of the perfect cubes, I think. 3 squared is 9. Right? So a cube root just asks you what times what times what gets you back to that original number. Let's do like 2 more rows, and then maybe we'll save the other ones till, well, I can make another practice too. Let's do up through number 7 together, and then maybe you can try the rest. Let's see. So I've got the 5th root of 32. So what number times itself 5 times could give you 32? So if you started with 1, 1 times 1 times 1 times 1 times 1 is just 1. But what about 2? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, right? So the 5th root of 32 is just 2, and then I need to square the 2. So 2 squared is 4. So far, those would be questions that you could do without a calculator. Because or else you could just type them into the calculator and You don't have to evaluate them. So this is just asking you the square root of 49. What is the square root of 49? 7. This one's just asking you the square root of 9 cubed. Now, if you switch it around, let's pretend you forgot what you were doing for a second, and you put the cube root of 9 squared. We don't know the cube root of 9. 9 is not a perfect cube, because something times something times something can't get you to 9. So you wouldn't want to do the cube root of 9, so you'd say, oh, it was the square root of 9. What's the square root of 9? Square root of 9 is 3. And then what did we say 3 cubed was? 3 cubed is 27. All right, let's do 7 together, and then you try the last like 6 problems on your own. Should have enough time. What time do we go till? 57, right? So we have like 5 minutes. I have a negative here. Huh? 4 minutes. So I'll do 7, you do 8 and 9, and we'll stop. How about that? So number 7, I'm taking the cube root of a negative number. Is that allowed? Could I take a square root of a negative number? I can't take the square root of a negative number, but I can take the cube root of a negative number, because negative 3 times negative 3 times negative 3 will get me back to negative 27. So it's okay if your index is odd, that you could have a negative number. So this is equivalent to negative 3, and I still have to raise it to the negative first power. Does anyone remember, what does the negative first power do? Flips this over. So it puts this in the denominator. So I would have negative 3 down in the denominator. So 1 over negative 3. So it would come out to negative 1/3. Okay, you try 8 and 9. I'll give you 20 seconds to try 8 and 9, and we'll see if we get the same answer. And then we'll do 10 through 15 next time as a warm-up. So we should set up number 8, the square root of 4, and then the negative third power. What is the square root of 4? And then what is 2 to the negative third power? So that's going to flip it over. So 1 over 2 cubed. And what is 2 cubed? What's 2 times 2 times 2? No, 2 times 2 is 4, times 2 is 8. So I'd get to 1/8. So to me, number 8 is one of the hardest, because you got to take a reciprocal and the 3/2 power. What's 0 to any power? 0 times itself is 0. So be careful. If 0 is the base, the answer is 0. All right, the end.